Hello class, this is CSE-5250, sections 2 and 60, week 3, spring 2026. I'm Giovanni Orijuela, and this is a continuation of the previous set of slides from week 2. So we began our discussion on chapter 4 with a Hello World program. Now we're going to move on to writing a program that estimates the value of pi given a summation. So this corresponds roughly to section 4.4 of the book. This is our infinite sum that we're going to use to estimate the value of pi. There is a serial implementation, so how's about just for fun, let's write a serial implementation for this pi estimating program. Which, oh, by the way, you're actually supposed to, as part 1 of your first programming assignment 1, you're also gonna have to write a serial implementation, basically single-threaded implementation of this exact program. So let's do that really quick. So I'm gonna create a new program, call it pi. Now that's open in terminal, vi pi serial.c. Press escape, press escape, :wq to create a new code file. There's no code in here just yet, so well, most of the code, the bread and butter of the code you're to write is in this section here. So we have a factor that must alternate its sign, so it's positive 1, then negative 1, then positive 1, then negative 1. We have a for loop that adds one term after another, and then we have to calculate the value of pi by multiplying that sum by 4, and then we get to print it out. So let's try it out. I guess the one thing we have to we're gonna copy from our Hello World program is this int main with the command line stuff here. I'll paste that there. And then although we won't need all of these libraries here, I'm just gonna copy paste them. There we go. We don't need the pthreads library just yet here. Pi estimating program. Alright, so let's see. The one thing we will need to copy from, the other thing we need to copy from the Hello World program is this portion of the code that gets us the number of threads, but we're not working with the number of threads, rather we are get the number of terms to add from the command line. We could just define this as a global variable, or not. Either way, it doesn't hurt if it's a global variable or if we just define it within the main function. I'll just define it as a global variable because I just copy-pasted it as such. Let's call it n because that's what it's going to be called in the slides. But if we're gonna define it as a global variable, we may as well define our sum as a global variable as well. So alright, let's continue. So now we have the number of terms from the command line. Let's just go ahead and write the for loop. So plus plus, but I'm also going to type in comma. Factor equals negative factor. What is factor? Well, we actually haven't defined that yet. So, we have to define what factor is. That is just a floating point variable. Double factor equals 1.0. I already have a sum variable defined up here. Don't forget that semicolon. There we go. So I can just simply say sum plus equals factor divided by 2 times I plus 1. Then I can say double pi equals 1.0 times sum. Then I can say printf the estimated value of pi is, I'll just copy that here, paste it here. Percent %d, no, percent %f. Return 0. There we go. Let's try this out. So of course, this is just a ordinary serial implementation of our pi-estimating program. Therefore, we don't need that entire command to compile it. So that would just that command was previously this long command gcc-g-wall. We can go a little simpler with compiling this one. So that would be gcc-o pi serial pi serial.c, press enter. There we go. Now if I just do /pi serial, I get a segmentation fault because it did not specify how many terms I want to use, how many terms I want to add. Let's try it again and do like 100 terms. We get 3.131593. That's a terrible estimate of pi. It should be 3.14159 and so on. I can do it over and over again and still get a poor estimate of pi, but if I add more terms, say 100,000 terms, it becomes more accurate. So 1.141593 with what is that? 10 million terms? 10 million terms. Alright? We have a serial implementation of a program. Let's see what happens if we try. Let's go ahead and parallelize this. So running the serial implementation is part 1 of your PTAR's programming assignment 1. Part 2 is to parallelize it. Okay. Going ahead with making a copy of our pi-estimating program, let's just call it pi. Let's open this up. And now you're allowed to follow along with these slides just to get started with what to do. But if you feel like you got a good handle of what to do, then feel free to continue with the programming section as you normally would. Of course, now we need ptr.h. For our global variables, we need sum and n, but we also now need our thread count. So int thread count so let's just comment this. So those are our global variables. Now we need to add a function prototype for our thread function. So that is we're going to call this thread sum. The return type is void star as before, and we are passing in a rank. That, remember, just pretend that rank is just the thread number. So thread 0 of 1, no, thread 0 of whatever, however many threads we have. So void star rank. Alright. In the body of the main function, we're gonna have to add several things. So let's create a pthread t star. That is our thread handles after all. Alright. We can't allocate memory yet until we know how many threads we're going to run this program with. Here we're going to get the number of terms from the command line, but we also have to get the number of threads from the command line. Because we need two things now, this program, we have to pass in two values. The first one is the number of threads, the second one is the number of turns. In the slides, I have it set up such that the thread count is the first thing you pass in, the term count is the second thing you pass in. So thread count equals strtol argv1 null 10. That means this should be n equals strtol argv2. Alright, now that we know how many threads we're running with, let's allocate the necessary memory. So thread handles equals malloc thread count times size of pthread t. There we go. So all of this code here that I highlighted that was calculating the value of reply, I am just going to delete all that for now. Instead, I'm going to add in the two for loops from our Hello World program, one with pthread create and the other with pthread join. Paste that in there. We are going to call the thread sum function. So we're in the for loop that creates the threads, instead of hello, it's thread sum. This line of code that prints hello world from the main thread, we don't need that anymore. And the part of the program where we have pthread join called within a for loop, keep that. So now we can deallocate our thread handles, because at that point the program is done. But before the program ends, let's print out the estimated value of pi. So what I can just do is go back to the serial implementation, copy that, paste it here. There we go. And oh yeah, of course, we have to write the thread function itself. So void star thread sum void star rank. Now there's quite a few things we need here, mainly because we are having each thread calculate its own portion of the sum. It's set up so that each thread calculates a block of the number of terms we have. So they're all consecutive. That means each thread has its own starting and stopping position. So we have long my rank, which again was just something that we passed in, but we have to convert it back into a log. Long I, which is just something that we're going to use as part of a for loop. It's long because an int might not be large enough for having it. An int might not be large enough, so long is just another. It's a larger integer data type, but the size of that depends on the computer itself. There is another alternate set of data types we can use that is guaranteed to be the same size regardless of the computer itself. But for demonstration purposes, I'm just going to go with long. So we need to calculate my n. That's just however many terms the thread is going to add. So we can just simply calculate this as n divided by thread count. So if we have 100 threads, if we have 100 terms and there are 4 threads, that means my n is going to be 25. Next is long my first I. So this is going to be this is going to be different for each thread. As I've shown in the slides, if we have, say, 100 terms and 4 threads, thread 0 is going to start at term 0 and at term 24. The thread after that is 25 to 49, so on and so forth. So that would just simply be my n times my rank. And then my last I, it's just going to be my first I plus my n. Alright? If my first I mod 2 equals 0, vector equals 1.0. This is because this is an alternating summation. This is just to make sure that the starting term that this thread is working with starts with the correct sign. So that's what this line is for. Else factor equals negative 1.0. So I can just comment this. Alright, so that if else thing, that's just to make sure that the sign of the first term is correct, so that every successive term alternates sign. So positive, negative, positive, negative. So now we have the for loop in which each thread adds a consecutive block of terms from my first I to my last I. So here we have for I equals my first I, semicolon, I is less than my last I, semicolon, I plus plus, also comma, factor equals negative factor. So all of this is modeling the serial implementation in which we have I plus plus and factor equals negative factor. Again, this is just to make sure that the sign of each term alternates. We're almost there. So let's do sum equals, plus equals factor divided by 2 times I plus 1. And then return null. This is just gonna add to the global variable sum. And then once each thread is completed, the main thread is gonna wait for each thread to finish running, and then join back with the main thread, and then after that, we can print out the estimated value for pi. This isn't quite right here. So estimated value for pi, but I did not define what pi is. I'll just copy this line of code and paste it down here. So pi is going to be 4 times the sum. Alright, let's try it out. I have a terminal open up here, so let me just clear. So the command to compile is going to be that gcc-g-wall-o. I've called the program pi. I'm gonna call the program pi, and the source code file is pi.c. Okay, there is a bug in the program that I have to fix right now. Factor undercleared. Let's fix that up. There we go. Let's try that again. There we go. Type in ls. There we go. There we go. We have our pi estimating program. Let's now do /pi. If I don't pass in anything, it's gonna segfault. Alright, so let's remind ourselves of what we are passing in. argv1, that is the thread count. argv2, that is the number of threads. So let's do /pi 4 threads, 100 terms. Estimated value of pi is 3.131, such and such. If I do it again, and again, we have the same result each time. Alright, let's try a more accurate estimate. So let's do like 1 million terms. You know, something is up. You see it? I'm adding 1 million terms across 4 threads, but I am getting a different result each time. What's up with that? And then, what the heck happened here? How did I get this? How did I get an estimate that is way off? How did that happen? I guess one thing we can also try is to run the program with the obscene number of threads, say /pi 100 threads and 1 million terms. Now we have an estimate of pi that is accurate to 2 decimal places, but it's still wildly changing from run to run. So what's going on with that? What's going on here? As a sanity check, let's also try it once more with just 1 thread. So if it's running with 1 thread, it should operate the same as it did with the serial implementation. So if I press that and just run it multiple times over, we have 3.141592. That value isn't changing from run to run. So something is going on with the parallel implementation. So, if you've taken operating systems in the past, and by this time you likely will have, you might realize that we forgot something, and that is, we forgot to enforce mutual exclusion. So, this is also going to be a review on race conditions and critical sections and mutual exclusion. So as we've seen, every time we run the program with the same thread count and the same term count, it might change from run to run. So this is going to be a review on race conditions and critical sections. So what's happening is we have a shared variable that's being accessed by more than 1 thread. So thread 0 adds, let's say thread 0 is trying to access the shared variable, but so is thread 1. both are trying to add 3 and 5 to the shared variable, the expected answer is 38. That's not what we get. Neither thread knows that there's another thread adding to the same variable, so both threads access the shared variable at the same time. They each calculate 33 and 35. Neither one is correct. Say thread 1 writes to the shared variable, and then thread 2, thread 0 and thread 1, because it starts from 0. We not only got the wrong answer, but we got 2 wrong answers, and we lost one of them. That's the essence of a race condition, which only happens when threads are trying to specifically write to a shared variable. What we need is a means of keeping threads from reading the shared variable while another thread is updating it. That's called mutual exclusion. So in our pi program, having a race condition means we are missing some terms in our calculation of pi, not by a lot, but we don't want the result to change each time. In your case, you might need to get your term count to be a large number to even see that there is something wrong. So, in the instructions for programming assignment 1, it will flat out say that there are bugs in this program, but that's actually fixing it is the subject of the next programming assignment. Well, there are actually even more bugs than that. Of course, we have the critical section. We have the bug where we have no mutual exclusion, but we also have another bug in which we have the number of threads must perfectly divide the number of terms. And if we don't have that happening, we might end up losing some terms. That is yet another bug that is actually going to be fixed as part of the next programming assignment. So, what I'm actually going to do is I'm going to preemptively give you the next set of slides. It talks about a few ways to fix our lack of mutual exclusion through a busy wait, and then through a mutex. And then it talks about a couple optimizations that we can also do to the program to, once and for all, fix all the bugs, but also demonstrate that through parallelization we can get it to run faster. So these are the slides that I will be uploading momentarily. I'll have yet another complimentary video in which we talk about these slides more in depth. Okay? Alright, so that's going to be it for this video. It's pretty short, but this video is just here to get you started with your first official programming assignment. Remember, programming assignment 0, that is just a Hello World program. Alright, that's going to be it for this video. See you next video. Take care. If you have any questions, be sure to let me know. See you next video. Bye.